Okay, great. Well, thanks for having me. I'm sorry I cannot be around in person. I'm gonna switch gears now a little bit because, in contrast to Alexis, who focused really on the high energy particles, our study here aims for investigating large number of SolO energetic electron events, even the less energetic ones. And we are using for that the combined in situ and remote sensing observations from SolO Orbiter. And I'm giving this talk on behalf of a joint working group that originally consisted just of members of the STIX and DPD teams. But as you see now on the logos, it has grown significantly since then. So we now contain quite a significant fraction of the instruments on SolO Orbiter. And as you see on the large number of collaborators, this is very much a team effort. I don't need to introduce SolO energetic electron events to you. Let's just say that there are still some discrepancies we see between the electrons we observe in situ and the events on the sun. There is a lot of evidence that at least a group of the energetic electron events, the impulsive events, should be more closely associated to solar flares. However, when we compare them to flare signatures, we find numerous discrepancies. One of them are onset time delays. So if we infer the injection times at the sun, these seem to be delayed from type 3 bursts or hard X-ray flares, often by 10 minutes or more. And if we compare the actual spectra of the electrons we observe in situ with the spectra which we infer from hard X-rays for the electrons which interact at the sun, then we find that they are correlated. So the two particle populations have something in common. However, they do not agree to the emission models we have. In particular, when we observe hard X-rays, this should be usually dominated by thick target emission. So our spectra should end up here, but they don't. So basically the particle spectra in space always harder than we infer from hard X-rays. So the question, of course, has for a long time been, is that effect or the different effects caused by the injection of the particles? So is the spectrum of the electrons which escape to space really different from the ones which remain on the sun? Are they really accelerated, delayed? Or is it more likely an effect due to the propagation of the electrons in interplanetary space? So far, it has not been, we have not been able to distinguish those two effects. Now, of course, with SolO Orbiter, we can address this issue because with SolO Orbiter, we can sample those particle events at different distances from the sun. And therefore, at least in principle, we have the opportunity to disentangle injection from propagation. Secondly, of course, SolO Orbiter has the advantage that it combines all the essential assets we need to study these phenomena on a single platform. So how do we do it? We start, of course, with the observation of in situ electrons with EPD, which gives us timing fluxes, spectra, and anisotropy, as well as the composition of the associated ion events. Then we have STIX on the remote sensing side, which gives us the timing fluxes, the spectra, and also the source location of the energetic electrons accelerated at the sun. We can then link those two regimes by using the radio spectra from RPW, which indicates the presence and also the timing of type 3 bursts, which sort of trace the propagation of the electrons from the sun into interplanetary space and finally to SolO Orbiter. These observations are supported by the UV imager EUI, where we look for associated events like UV flares, deaths, and also CMEs. The coronagraph METIS, which also gives us CME association and characteristics. Now we also use SolO High. And finally, for studying the interplanetary context, which is of course important since the particles have to propagate through interplanetary space. We use SWA and MAG to characterize the solar wind and the interplanetary magnetic field. Crucial thing, of course, is to associate the solar event with the in situ particle event. And this mostly rests on inferring an ejection time. So here we use two different techniques, simple time shift analysis, where you look at the event onset at a specific energy, then you know the speed of the particles. You have to assume a propagation length. Here we use the Parker spiral, which is constrained by the measured solar wind speed at solar orbiter. And in events where you see a velocity dispersion, like here, so here you have high energy particles down there, low energy particles here. If they're accelerated at the same time, high energy particles will arrive at the spacecraft first, low energy particles later. And then you can fit this and get both an onset time and also a path length. So we don't need to assume anything about the path. And this we then compare with the X-ray light curves we get from STIX. And in this case, you see that both inferred injection times are closely agreeing. And it appears that indeed there is a STIX flare, which is a candidate as a source of these particles. However, this situation is not always as clear-cut. Therefore, it's always good to also consider the type 3 bursts we see in RPW. So let us zoom into this event. Here you see a strong type 3 burst observed from RPW, which is consistent in time with the onset or injection times, rather, injection times inferred from EPD. And this points to this time here. This line here indicates the major non-thermal hard X-ray peak in STIX. But you see that there was actually a peak before, which was a little bit smaller. However, both the EPD times and the type 3 would suggest that it's actually this hard X-ray peak that is associated with the interplanetary electrons. And this shows you how we can use the additional information provided, for instance, by RPW, to identify the correct counterpart. Our main goal is to provide a joint event list or catalog that contains all energetic electrons that are clearly identified by EPD. Up until now, we've almost completed the catalog till the end of 22. But the idea is, of course, to update it regularly and keep track of all the events we see during the mission. Then we look for the associated STIX and UI flares, the METIS and SolO high CMEs, and the RPW type 3 bursts. We also include information on the magnetic connectivity, which is provided by our colleagues in Toulouse using the IRAP tool. In total, the list encompasses about 70 parameters for each event. And at the moment, we are very busy to finish that and make a first publication and make this available to the community. This is just for illustration, a glimpse into the list, and it doesn't show you all the parameters here. So in this talk, I want to just give you a few general results on the statistics we have so far. So let us start with the event occurrence from November 2020, which was the time when STIX and EPD observed for the first time together. Until the end of 22, we have observed about 300 energetic electron events with EPD. Here you see the distance from the sun, and here you see the number of EPD events per month. You see that solar activity is increasing here. And you also see that the number of events is not really correlated with distance from the sun. It is mainly driven by active regions which are particularly productive in solar electron events, which for some reason have a better connectivity to interplanetary space and to the space. These are the distances we have sampled so far. So we go down to 0.3 AU up to 1 AU. And here we see that about a quarter of our events are actually from closer than 0.5 AU. So we have a decent number of events close to the sun. Of course, we spend most of our time farther away from the sun. Therefore, more of the events are from larger distances. Let us look into composition here. So that's the composition of the ions that are associated to the electron events. We group that in the classical groups of impulsive and gradual that Alexis has also already introduced. If we do that, impulsive events which are enriched in helium-3 and iron are about 3/4 of the events, 20% gradual events, and a few intermediates and events where we cannot determine that. Anisotropy, that is determined from the EPT sub-instrument of EPD. And this is just a rough measurement whether the anisotropy is large, medium, or small. In a significant number of events, we cannot measure it.
We're losing you. We cannot
Sorry?
really hear you. Sorry, we were losing you a bit now.
Is it better?
Maybe, yeah, it's better. Maybe you have to speak to the microphone. So.
Yeah. So anisotropy, you see that more than half of the events have at least medium or high anisotropy. That means there's limited scattering during the propagation of the particles. And about 20% of the events, we cannot really determine it because the energies, the event doesn't reach the energies of heat. Interplanetary context is of course important. And if we look into the solar wind conditions associated to our events, we see that in 50% of the events were in slow solar wind, 20% fast solar wind, and about a quarter of the events, there are some more complex structures. And this is split here into the different subgroups. So more than half of them are associated with the transit of a CME. Then we have stream interaction regions, the heliospheric current sheet, and small-scale flux. And of course, in those events, we have to be more careful when we associate the in situ events with solar events because the conditions are more during propagation. How about the flare association? So nearly 90% of our events are also associated with STIX flares. But there are 20 events where it's clear that there's no response in the STIX light curve. So these events have no hard X-ray counterpart. On the EUV side, about half of the events do show a flare in EUV or a different kind of eruption without a flare. Again, a significant number of events which do not show any response in EUI. And in a third of the events, we do not know. And this reflects the duty cycle and also the cadence of EUI, which during these synoptic time windows is quite limited. So we miss a lot here. Whereas with STIX, we are operational in nominal mode for all the time, and therefore we catch most of the events. The same, as I said, for EUI is also true for METIS. So in only 20% of the events, we do see CMEs, larger fraction definitely without CME, and an even larger fraction where we do not know from METIS because of the limited duty cycle. And this, of course, when we want to have statistically valid outcomes on CME association, we need to consider other data sources as well, because just from solar orbit, this will not be sufficient. Finally, type 3 bursts as determined by RPW. In most cases, we do see them. Here are the single ones. Most of them we see multiple type 3s, a small fraction even type 3 storms, so many type 3 bursts. And there are a few events where there's no response in rate. With STIX, we can also determine the source location. This shows you the location on the sun for the STIX flares that were associated with the impulsive events in blue, with the gradual ones in red. You see that they're coming from the two activity bands, of course. And if you look into the blue circles, you see that there's a east-west asymmetry. So most of the blue ones The impulsive events are actually coming from the Western Hemisphere. We all know that due to the Parker spiral, we should be magnetically connected to the Western Hemisphere. We can look into more detail here and compare the source locations with the predicted foot points of magnetic connectivity as given by the IRAP tool. So this is the difference in longitude of the stick source versus the magnetic foot point, and this is the difference in latitude over here, again split mainly into impulsive and gradual events. And what we clearly see here is that the impulsive events are highly peaked around 0, so they are close, the sources are close to the predicted magnetic foot point, whereas the gradual events have a much flatter distribution. So for them, it appears to matter not very much where on the solar disk they originate, while for the impulsive events, it makes a big difference. And this would be, of course, consistent with the picture that the impulsive events are more associated with solar flares, so highly localized in space, whereas the gradual events are more consistent with acceleration at an extended structure, such as a CME-driven shock. Let's look into timing. So this is now the time between the injection time derived from time shift analysis and the Sticks peak. If it's negative, then the injection is earlier. If it's positive, then the injection is delayed. So here we again see that the impulsive events are quite highly peaked, around a few minutes delay, whereas the gradual events again have a much flatter distribution. And also a longer average delay here, 13 minutes as opposed to 5 minutes. So it seems that the impulsive events show a significantly better temporal association with flares. And here we use the VDA injection, which should provide more accurate values because we do not assume a path length here. On the other hand, we can do that only for a smaller number of events, but in principle, we see the same, highly peaked for the impulsive events with a short delay and broader distribution for gradual events. So again, better temporal association for the impulsive events, which is of course, again, consistent with acceleration at the flare. And finally, for these histograms, this is the time difference between type 3 burst onset and the non-thermal Sticks peak. And you see that in most cases, they are nearly simultaneously with a few outliers. And of course, associating that is not always so clear-cut because we have Sticks flares with multiple hard X-ray peaks. We also have events with multiple type 3 bursts. So if you want to look into more detail, you have to start filtering your events and, for instance, consider only events where you have one non-thermal Sticks peak and one type 3 burst. But I won't go into that now. So far, basically everything what I have shown has been done before, maybe not with this high quality of a data set. But what I show now is new. This is now the time difference between the injection time and the main Sticks peak, but plotted as a function of distance from the sun. And let us start with the impulsive events. They do not show any correlation. So the impulsive events, most of them are significantly delayed. This is again using VDA injection time. But there is no correlation with distance. If we go to the impulsive events, there is still significant scatter. There are a few strong outliers, but there's a weak trend here of an increase of apparent onset time delay with distance. If that is statistically valid is of course the question. So what we can now do is of course start filtering the events. This is all the events we have. So let's try to see what happens when we only consider the highly anisotropic events. So events which have not experienced much scattering, they should be well connected to the sun. If we do that, we see that the correlation has increased. It's still quite modest, but we have removed the very large outliers. And this could be taken as the first evidence for propagation effects to act between 0.3 and 1 AU. What we can now do is, of course, filter the data according to different aspects. For instance, only look into the events where we are in quiet interplanetary conditions, or only look into events where the separation angle between the stick source and the magnetic foot point is low. And if you do those different things, you always end up with correlations that are more like looking like this. So not extremely good correlations, but rather consistent, regardless on which aspect you really filter on. And the same thing you can also do with the type 3 bursts. And this, for instance, shows you the time difference between the VDA injection and the type 3 burst onset versus distance. And here again, only considering the events which have a high anisotropy. And basically this confirms the result we got with sticks, and the correlation here is even a little bit better. So to summarize, from the basically first 2 years of SolO orbiter being fully operational, we have observed about 300 electron events, sampled over distances between 0.3 and 1 AU. We have found multiple strong evidence that the impulsive events, impulsive in terms of composition, are really associated with solar flares, and this includes the correlations with the location of the events and also with the timing. And finally, we have found some tentative evidence, I would say, for the role of propagation effects in the injection or the apparent injection time delays. Our next steps in this large joint working group of different instruments from SolO Orbiter will be to publish this joint event list together with the first statistical results. And we are working heavily on that right now. Just 50 minutes from now, we have the next telecon, so I'm afraid I will have to leave you then. On the more longer time scale, of course, we will perform a spectral analysis, both of the EPD in situ spectra and of the STIX hard X-ray spectra, and compare how the spectra of those two electron populations relate as a function of solar distance. Again, this is the first time we can perform a study like this with SolO Orbiter. And finally, of course, we are also very interested in including in situ electron observations from other locations in the heliosphere, from other instruments, so that we can study also things like the lateral extent of the electron beams or their evolution with distance from the sun. So thank you for your attention, and I'll be happy for questions.
Thank you very much, Alexander. Questions?
Yeah, hi, Alexander. This is Bernd speaking.
Hi, Bernd.
Hi, thank you very much for this very interesting and talk. And I have several a question. First of all, the electron event you investigated here, the energy was 100 keV or was it below?
Basically, we aim for studying all electron events which can be identified by EPD. So there are events included which do not go beyond a few tens of keV, but there are also events which extend well above 100 keV. But I would say the focus would be the energy range which is covered by EPT here. So tens of keV to up to 1/200.
So my question would be, first of all, if you determine the VDA, even if you take high anisotropy at low energies, there might be energy exchange. So that means the low energies may come from higher energies. Would that change the picture?
Let's look at this example here. So basically, here is the cut, right, between STEP and EPT. And
Mhm.
could you make your point again, please?
So that means that the low energies would come in principle later, so they would move to the right a little bit,
Mhm.
and then the thing would be flattisher, and you would even be getting closer. Is this something which could be systematically um, uh, helps to understand better these differences,
So
this distance?
could you explain what would cause this effect
So
here?
the thought is, so if the particles lose energy on the way between 0.3 and 1 AU, or
Yes.
on the full way, so you
Mhm.
would attribute the energy at 1 AU to 100 or 10 keV, but most of them comes from 15 keV. So they are coming in principle from a higher energy. So your gradient is something which has to do with the energy loss of this particle.
So you're thinking about energy loss due to wave-particle interaction primarily, or what's the effect you're thinking about?
Yeah, well, you're running in an expanding medium. So
That's something I will discuss in more detail with the colleagues from EPD. I cannot give you an answer right now.
okay, and what did I have? Yeah. So and these, I mean, it's quite astonishing how good the VDA and also the other method now goes with the onset in the sticks data. Is
Mhm.
that an instrumental effect that we are now having better instruments, that this looks much, much better than before? I mean, in the sense that it's getting closer to this, or what is the reason for this?
I mean, there are a few outlier events which were not part of, I think, let's see. For the time shift analysis injection, there have been a few outliers which have large injection time delays. For VDA, this is everything we have. So I don't know. I don't know why it's now looking better. We certainly have a much better coverage from the hard X-ray side. So I remember the studies that have been done before, also one where I was involved in, where we compared electron events observed at stereo with RESI data. We basically had the whole mission, and there were just 20 events or so which were observed by both instruments. It really helps to have your instruments on the same spacecraft to basically achieve an effectively much larger duty cycle. And then I think it's really also dependent on the effort you spend in associating the events. So if you just do it automatically and go for the closest major flare, you will miss small scale events. And this you really have to check by eye. So we have really validated all our events by eye and also by comparing them with the radio spectra, which gives an independent line of evidence. So I think it's really it's the instruments that are available all the time from the same spacecraft, and it's the effort that is put into looking at the data.
Yeah, thank you very much, Alexander.
Thank you.
Any other questions here in the room? No, in the chat?
I have a question.
Yes.
Go ahead.
So on the plot with the delays that you showed us, I think it was the last slide. Well, not the last one, the previous one that contains all the events. So if you make this, let's say, filtering of events instead of considering the anisotropies, using the connectivities and
Yes.
let's say filter the events into two categories, so well connected versus poorly connected. This is is this going to show similar results? I mean, I wonder if this would be also the case.
Yes, this is something we are working on right now because we do not have for all our events now the source positions and the connectivity. So there's, I think 50 events or so are still missing. But this is work in progress, and this will certainly be also part of the first results that that we will show.
I
I agree.
this-
That's a very important point.
I think this would be an interesting feature, and also, you know, what I'm thinking of is by separating, you know, the sample into two populations and make, let's say, two distributions of the time delays. Then from the distribution characteristics, you may be able to say if those two are completely separate statistically or there's an overlap, and you know, and then discuss if this is statistically significant or not. This is what I'm thinking of. So I think this has a good potential. And another question is, have you also utilized radio data in the respect of the presence of Langmuir waves? Is this possible to include something? Because, you know, in some cases, this can be a very helpful indication that you were connected or you were not connected to the source region. And that also may give some important information. So I was wondering if this is also something that you will consider or might consider.
Yes, so the presence of Langmuir waves is actually one of the columns in our event table, and this is again this is not complete now. We have completed checking for the type 3 bursts. Langmuir waves are not yet complete, but we intend to have them as well. Yes.
I see. Interesting. Yeah. Thank you.
Thank you very much.
Excellent. Thank you very much.
you.
Yeah, do you have a question?
Oh, sorry.
No. Okay. Thank you, Alexander.
Thank
We are
you.
going to